Alright, this is a question from part C of CSIR 2023 question paper. And the question says this: F from R4 to R mapping, which is given by f x y z w is equal to x w minus y z. We are asked about which of the following statements are true. Okay, so first part is f is continuous or not. We can easily see that this function is a polynomial function in x, y, z, w. Therefore, it is continuous function. This is not a big deal. Okay, so first part is true. Now for the second part, we have u is defined as x, y, z, w belongs to R4 such that x, y plus z, w is equal to 0 and x square plus z square is equal to 1. X square plus z square is equal to 1. Also, y square plus w square is equal to 1. So this is a set U. These are all points in R4 such that xy plus zw is 0, x square plus z square is equal to 1 and y square plus w square is equal to 1. We are interested in if f is the function f here given above is uniformly continuous on U or not. Okay, we will use a result that if a function this is a famous result that if a function is continuous on a compact set, then it is uniformly continuous too. Okay, so for that, to use that, we need to show that U is a compact. We will show that U is a compact set. Okay, as U is a subset in R4 and we know in Rn a set is a compact if and only if it is closed and bounded. So all we need to show that U is closed and bounded. Okay, first of all, to see U is bounded, we take norm of any elements x, y, w, 2 norm and square it, Euclidean norm. What will it give? X square plus y square plus z square plus w square, and its value is 2. Thus, every element in U has norm 2. So it's a bounded set. As we show, for any vector x belongs to U, the way U is defined, x norm is less than root 2. Thus, U is a bounded set. Well, let me write U again. It was x, y, z, w belongs to R4 such that x, y plus z, w is equal to y plus z, w is equal to 0, x square plus y square is equal to 1, z square plus w square is equal to 1. Okay, we are interested to show now that U is a closed set. We need to show that U is a compact set. We have shown that until now that U is a bounded set. And now to show the closed set. Okay, just observe this. Just observe this. X, y plus z, w is equal to 0. We will use this. We define a function phi x, y, z, w. which is xy plus zw. Okay, and note that all the zeros of phi are satisfy this. All zeros of phi, all zeros of the function phi satisfy this property. Okay, now phi is continuous function, again polynomial. Okay, so phi inverse 0 is a closed set, and phi inverse 0 contains all zeros of phi. Phi inverse 0 is a closed set. Okay, in a similar way we define another function, let's call it psi. Psi xyzw is equal to x square plus y square. Okay, it's a continuous function, again polynomial, and phi inverse 1 is a closed set. And what does phi inverse 1 indicate? Phi inverse 1 consists of all elements in R4 which satisfy this property. Okay, so we have phi inverse 1 is a closed set. Now in a similar way we define let's say alpha x y z w, which is equal to z square plus w square. Again it is a continuous function, and now we consider alpha inverse 1, which is a closed set. Okay, why are all these alpha inverse, phi inverse 1, alpha inverse 1, phi inverse 1 are closed set? Because 1 is a closed set and inverse image of a closed set is a closed set. Okay, now I am writing the main claim, but I am going to say that U is phi inverse 0 intersection psi inverse 1 intersection alpha inverse 1. Okay, see, verify it, no issue in that. Where phi is here, like we have defined here, this is phi and this is psi and this is alpha. We have simply the conditions that were given, we have defined a function according to them. These three conditions were given, we define a function according to them, and we take inverse images of this, the values that are given, condition are given, and we define U. We find out that U is phi inverse 0 intersection psi inverse 0 intersection alpha inverse 1, and these all these three are closed set, therefore U is a closed set. We have shown that U is a closed set. We have already shown above here that U is a bounded set. So U thus U is a compact set, and continuous function of a compact set are uniformly continuous. Therefore, second is true, F is uniformly continuous on U. Now we consider third part. Now we consider the third part, in which B is defined like this. And we are the question is f is uniformly continuous or not on V. Okay, first of all, what was f? If we recall that it was x was y w was x y minus z w. Okay, right, sorry, it was, I think, okay, sorry, it was x w minus z y. If you just see that it is a determinant function, like if x y z w, we take its determinant, we will get x w minus z y. So we are all things is doing above a determinant function. Okay, now if we put okay x w, now as x is equal to y, so this become, and z is equal to w, this become w, w x, they are equal in reals is 0. So f is 0 on V, as f is a constant on V, it is uniformly continuous. Constant on V, thus f is uniformly continuous on V. Alright, so according to the question, third is also true. Okay, now we get into the fourth part. Now we are in our fourth part. Here w is equal to x, y, z. W belongs to R4, those elements such that x plus y z plus w lies from 0 to 1. Then f is bounded on w. This is we need to show. Bounded on w or not, we are interested in that. Okay, first consider let x is equal to, we take it as say 1 minus n, and we take y to be n, and we take z is equal to 0 and w is equal to 0, n belongs to natural number n. Then x plus y plus z plus w is 1. Okay, thus all such elements all such x y z w belongs to w, capital W. Okay, because we can have one. All right, so what is the value of function in this case? Our f was xw minus zy, which will be, yeah, wait a second. Okay, sorry, let's take w to be n. Okay, that will be better. Let's take y to be 0 and w to be n. Okay, it's still x plus y plus z plus w is equal to 1, there is no doubt. Now xw minus zy, that will be equal to 1 minus n into n. Are you sure? This will be equal to n minus n square, which goes to minus infinity as n tends to infinity. Thus simply we can say that f is unbounded on w. Hence the fourth option is also true. Thus all the parts are true.